So David Metivier obtained his PhD in theoretical physics at the University of Nice in France with Julien Barré. He worked on the dynamics and statistical physics of mean field particle systems. He joined Los Alamos National Lab almost 3 years ago as a postdoc to use statistical physics concepts and tools such as synchronization, mean field, and uncertainty quantifications applied to power systems. So we are looking forward to your presentation, David. The floor is yours.
Okay.
Oh, David, yeah.
Okay.
We can see your screen, yes.
Okay, cool. So thank you for Line for the introduction and for the previous talk, which basically introduced already the technique. So I'll cover that fast. But the main difference with what Line is doing is that here, indeed, we try to do something efficient in the sense that it will scale to large network, as you will see. And we'll use some idea of sparsity to make the code faster. Yeah. So Marc, Vuffray, and Sidhant Misra are my co-authors. And let's start. Let's start. So here is the deterministic version of ACOPF. So you've seen it on and on, I guess. So you have the physical equation, you have the minimization of some costs, and you have the safety bounds that you want to satisfy. And here again, I'll emphasize what Line said before, but here everything is deterministic, and basically every variable in blue you try to find. If you put that in a good nonlinear solver, you find a local optimal solution or even global optimal solution. Now, if you add uncertainty to the problem, basically you can view your old variable are now functional of your uncertainty, where psi is some stochastic vector, and you want to solve the same problem. Here, the way we implement uncertainty is by zone. So we attribute one random variable to a zone, so that the whole system is random, but the number of psi is limited, because as Line told us before, it's really the bottleneck of the method. So now you still have the physical equation, but it's a stochastic version. You still try to minimize some objective, but an expected value. And you still have the safety constraint, which are now the so-called chance constraint, the dreadful chance constraint, because in general, that's what the hardest part is, to deal with that. So in Line's talk, basically they convert this into a deterministic problem with thanks to PCE, which is feasible to solve in a solver. So but here what we do is a bit different. So we turn that with we use PCE for this part, and to satisfy this part, basically we do some iterative method. So I would say in that sense our method will be faster, because we don't have to deal with this equation and the chance constraint at the same time. So in that sense it will be also faster, but also just this part will be faster. But the drawback is that we don't have everything in one code. Yeah. So in general, any uncertainty quantification method is like you have uncertain input. So you have some process and some uncertain output, and you want to quantify your output. So you can do Monte Carlo sampling, basically. So you sample this guy, solve that, and then have statistic on your output. But you can, so this part was a bit introduced already. You can do map y as a polynomial, and the first polynomial you can think of is like a Taylor-like expansion. And so if you find the coefficient a, b, c, basically, or a, b here, if you stop at linear order, you basically have an explicit expression of your output. But the point of polynomial chaos expansion, which is not related to dynamical chaos, but it's just the name at the time of this guy, how they talk about random processes. The idea of PCE is to do a smart polynomial expansion, in the sense that you use the prior knowledge on Xi that you have. For example, if you know Xi is normally distributed, you will use the appropriate basis. And you use orthogonal bases. And in that sense, you do a control expansion in Xi compared to Taylor-like expansion. And you can show that polynomial chaos expansion bases are the ones that converge the faster. If you look at this quantity, which is really the quantity you want to minimize, it's in stochastic problem, it's really this one. Compared to a Taylor-like expansion, this will converge faster. That's the point. So as Line say here, we do not linearize any physics, and we really try to capture the full nonlinearity of the problem. So as it was said before, and I'll say that a lot, I guess, in my talk, if you have now a lot of source of uncertainty, then your polynomial basis explodes. So you have degree 0, you have n degree 1 polynomial, n square degree 2 polynomial, etc., etc. So your basis can be like with 10 polynomials to 10,000. And here in this paper will be more on that, but we have another working paper where we are more working on this side of the constraint. So one thing that is really nice with that is that you have easy interpretation. So you know that if you look, for example, at this voltage here, you know that the Y1, for example, will tell you how much this voltage is sensitive to this uncertainty. And the degree 2 will tell you how much the correlation between these two affect this voltage. So you can build some physical intuition about your network. And you can guess that for very large network, for example, many of these coefficients should be close to 0. First, the degree 2 should be smaller, so smaller than degree 1. And then in general, a lot of coefficients should be 0. So that's the sparsity that you try to look for. And we'll use that. Then you can compute moment. I won't go on that because Line told that already. But now, how does it compare to PC, to Monte Carlo method, for example? So here is a kind of extreme example, but if you look at this voltage, for example, from the test case given by the Pegas project, you see that if you stop at degree 1, it's bad, and if you go degree 2, it's good, basically. So you don't need to go to degree 3. It doesn't add more information, and it's computationally much expensive. So we stop at degree 2. Yeah. So now, how do you find this coefficient? I didn't say how you find this coefficient. Is basically, the idea is you have your physical equation, stochastic one, and you have your basis, and you can project that. And at the end of the day, you have like you go from stochastic variable to deterministic variable. So in this simple example, for example, this stochastic equation, if you project it, you end up with new equations that are deterministic. So that's the trade-off. You go from something that a solver doesn't know how to handle to something that you can put in a solver, but which is much larger. And that's the trade-off, really. Now, if you go to like this line equation, for example, where you have quadratic terms, basically you will end up with large sums. And that's really what limits the PC method in its simplest form. Because here you have a summation, you have two series, basically you have a cross product, so it's very big in a solver. So at the end of the day, you convert your whole stochastic problem into a deterministic one, but this new deterministic problem is longer because you have L equation each time, and it's larger in general. So as I said, this coefficient, you have a lot of them, so that's a bit not cool. And what is nice is that you can compute them offline once and for all. And what we do, and that's the difference with the previous talk, is we can neglect high order. Because as I told you before, some coefficients are associated with degree 1 or degree 2, and you know that degree 2 must be smaller in your expansion. So if you have 2 degree 2 terms, you know it will be very small in general. And so you can safely remove a lot of this coefficient so that it's not as dreadful as this number. So now I'll describe exactly the algorithm we use. So first you have your stochastic power flow equation that you write once and for all into the PC basis. Then if you look at this picture, the idea is we do iterative approach in the sense that we first solve for degree 0, which is given by the ACOPF solution. The degree 1 is very fast and you can compute it and really the hard part is compute all these quadratic coefficient. So we solve the degree 1 and then we estimate the sparsity of the system by this simple thing, which is if the cross product here is very small, and this you can compute with the degree 1 only, then the degree 2 must be also small, so we put it to 0. So we have some threshold to do that, but that's the main idea of yeah. And here also the other main idea is to cut a lot of these terms. So with these two ideas, then we can solve the full degree 2 problem, but now it will be much more sparse. And the idea is that it's faster. So in terms of timing, here is the number of uncertainty, which is really the limitation in PC. For Monte Carlo method, it doesn't change too much. If you have 10,000 samples, for example. So here I'm still in this 1,000 bus Pegas test case. So the standard PC method, and I would say it's the one shown before, but without the change constraints, it will evolve like this in terms of timing. And our method, SPICE, is evolving like that, and so it's wow, I cannot say this word. So it's faster every time, and basically it's has the same accuracy as before. We can check that. So another advantage of our method is that it's kind of sensitive to the total fluctuation you put in the system. So if you put a smaller fluctuation, then it will solve consistently faster than the PC method, which is not really sensitive to that. It's not always the faster. So that's for the timing part. Now, how do we deal with the change constraint? Because we could solve that and then give that to an operator, but say it's very fast and nice. But if we don't solve the change constraint and satisfy them, then it's useless. So as I said, the picture is ACOPF will give you, for example, this point. Then we can do PC to get this histogram, for example, and find this histogram. And then if you look at your safety bound, it's here, for example, for this voltage. And what you would like to do is that you would like the bound to be here, to have only 2% violation instead of here it's maybe 25% violation of the time. So the idea of our method is to measure this distance and then shift the bound accordingly here in that direction. And then we can resolve a new ACOPF problem with this new effective bounds. And maybe the new ACOPF will be here. And then if we redo PC around this new state, then we find something, and the hope is that it will be just a translation of that, because we do small push. Basically, it should be some linear response. It could be something else. It could modify the whole histogram, but that's not what happened. So we can do that and check all constraint. So the point is that we can do that to all the change constraint at the same time. And if we do that, then we show, so it's not exactly what's in the paper, but this one is better, that with just one iteration of this algorithm, we basically find a feasible solution for the change constraint. Here, for example, it was like 2% only violation for all the change constraint. And in terms of cost, if you think of the ACOPF solution, here it's just plus 1% of what the cost of the ACOPF solution. So we can say it's not too bad. So basically it's the cost here. This cost is due to the fact that we have uncertainty in the system and we must pay the price for that. And yeah, so at the end of the day, PC, and that was already motivated, it's really nice. But the kind of new thing here, I would say, it's that it has an easy physical interpretation, and that we can use that to estimate the sparsity of the system beforehand. And then we propose a very simple algorithm to solve the change constraint. In the future, yeah, let's do a Julia package because people do that. And we are working on this kind of machine learning method to accelerate that. Thank you.
Right, thank you, David. So yeah, just.
I have a question if there is nothing else on the chat. Harsha here.
Yeah, I think that Harsha, you can go ahead first while people.
So this question is for both, Lina and to David. So if I understand correctly, once you do this polynomial chaos expansion procedure, you truncate certain higher order terms and you take only up to second order terms, and you solve this polynomial optimization problems using local solvers, right? Do you have any idea how good the quality of the solutions of this of IPOpt, how is it doing? So for instance, have you compared without chance constraint just for the nonlinear ACOPF with the global optimum or something like that?
I'm not sure. Yeah, Lina, you want to? No.
Oh, yeah, you can go ahead first, David.
No, I didn't hear very well. So that was
all right. Okay. Then I will maybe say something. So Harsha, the way I understand your question is that you're asking if by using a local solver, if that is causing problems for these type of problems, as opposed to like if we end up with local minima. Is that
okay?
Right, exactly. Because you're solving after at the end of the day or non-convex problems using local solvers,
yes.
right?
Yes, exactly. So I would say, I mean, this is, I mean, we don't know, right? I mean, it could be that this is causing problems, but I would say like we kind of, I guess we've learned a little bit that local solvers like IPOpt, interior point solvers, oftentimes do a very good job in terms of finding very high quality solutions. And if that would be the case for the deterministic ACOPF, I mean, particularly maybe with the type of method that David is using, I mean, it's essentially using that ACOPF as a basis and then making updates to it. And in previous work, but using very similar approaches, I mean, I think we've seen that, you know, the updates that you're doing, I mean, the first iteration doing a good step. Yeah, I mean, I think you could expect it to be kind of similarly good as the standard ACOPF. However, but for the polynomial chaos expansion, when you're solving it as a whole problem with all of the terms involved, there I am less. We haven't done any studies or that of that, whether we are getting more local solutions in that case.
I don't know, it may be worth, I mean, just a suggestion that it may be worth looking at some sort of a relaxation form of that polynomial for problem, and then maybe try to quantify the, you know, duality gap from upper bound and the lower bound of the problem.
Mm-hmm.
Yeah, I think in my point of view, it's really like the future of like this method is really to convert the whole stochastic ACOPF into a tractable, like deterministic ACOPF, if you want, with uncertainty. So if that's proved very effective, I think the future is that people working on ACOPF, like relaxation method and stuff, maybe will work on this new version of ACOPF with uncertainty and apply all the relaxation and stuff, all the nice methods they have to solve this new non-convex, nonlinear problem. And that's just my view of that.
Yeah, great. Yeah, thanks. Yeah, that's very.
Yeah, thanks, Harsha. I also just wanted to add, I think it's sometimes hard to find lower bounds on this type of I like finding lower and upper bounds is, I mean, when you have the stochasticity in there, can also be a challenge in itself. You have to think about it slightly differently. Okay, but there's another question here in the chat. A few ones. So Dan Moulton is asking, David, thank you for your talk. Very interesting approach. Have you identified any cases where the degree 2 PCE is not effective? In any such cases, would it be interesting to characterize if there are any physical aspects of the system of probability distribution that lead to poor performance of the PCE method?
So have I identified cases? Yes, and I guess it's thanks to Patrick Ponciati. Yes, because I look at two-bus case, because that was a question that was given to me at some point. And in the two-bus case, for example, you can find sometimes there is no feasible solution. And basically, if you are very close to that infeasible solution, then the system is very, very much nonlinear in some sense, and the PC fail close to that. But in general, for the test case, like well-behaved that we use, like this case, for example, I try to go very high uncertainty input, and couldn't find really. I guess, yeah, for too large input, then it just yeah, doesn't work, I guess. But I went to like 10%, like 0.1, for example, fluctuation at each node, and it still works well. So I would say it works well in a reasonable range.
Okay, cool, thank you. Okay, so I will give you like one more question. Sorry, we are also running a bit later on time here. So there is one question on computational times. Maybe you can answer that in the chat. And there is another question from Patrick Pansitisi, who is, do you think that ideas inspired by lasso or compressed sensing could be useful to find a sparse polynomial? Which orthogonal polynomials are you using? And do you believe that selecting another basis could help?
So the basis I use is the one that it's the best choice with if you know your xi, your distribution of xi, then there is no many choice of bases. You can choose, you know which one is the best. For example, if it's like a Gaussian mixture, xi, then you know the associated bases. So that is a given. So you don't have too much choice on that. You can try other bases, but the theory tells you that in principle they should perform poorly. Less better. Now, in terms of sparsity, yes, that's what we are working on, is basically using, instead of using the physical projection of every equation like that, we can just try to fit this polynomial basically we just sample from the Monte Carlo and try to fit the best polynomial. And then when you do that, you can add some lasso regularization and stuff, and then you can find a sparse solution. So that's what we are working on now.
Yeah. Okay. Okay. Well, thank you. Thank you so much, David. We really need to get going with the next presentation with Harsha. Yeah, we're running a little over time here after our some technical difficulties in the beginning. So, but yeah, so Harsha, please.